Okay, so we've now worked plenty of example problems from this opening section of the graphs of trig functions chapter. So this opening section on the introduction to the sine and cosine functions. We're ready to move on to the next section. But before we do, I wanted to post a few videos with problems like the one shown here. And the goal of a problem like this, what I'm trying to illustrate to you, is how the sinusoids are like the king of or queen of all periodic functions. They're the most fundamental. They're like the periodic functions. Okay, so I mean, we talked about there's all kinds of different periodic functions. You know, the heartbeat on a heart monitor. That's periodic, right? There's all kinds. Square waves. Triangle waves, etc. But the most fundamental, you could say the king or queen of all periodic functions are the sinusoids. And so another way you can look at it, you might be saying, well, what exactly do I mean by that? A good way to look at it is, so it's kind of like in probability and statistics. You know, if you flip a coin with no bias and you do that a large number of times, then over time, the ratio of heads to tails is going to approach 50%, right? If you do it enough times and there's no bias, it'll eventually approach, you'll get 50% heads, 50% tails. Well, anything in nature that is like just naturally periodic, and a good example of that is here, they say the temperature in Anchorage, Alaska. So they record the temperature every day. They get the average temperature every day and they record it. Then the next day they record it. Next day they record it. If you could record the temperature every day, but not just for a year, but for hundreds of years, thousands of years, and let's say there was no bias, there's no climate change, then over time it's like if you averaged all of that out, that would be something that's like kind of like naturally periodic, right? Well, if you did that, if there was no climate change, no external factors, and you over thousands of years, you kind of averaged out all of those temperature values and broke it all down into 1 year, it's going to be sinusoidal. The distribution is going to be sinusoidal, right? Anything that's just naturally, purely periodic is going to follow a sinusoidal pattern or some close variation of it. And so that's the idea I'm trying to communicate to you with these problems here. So yeah, it says the temperature in Anchorage, Alaska can be approximated by this function. This is just a sine function that's been scaled about the x and y axis, and it's been shifted along the x and y axis, where T is the temperature in degrees Fahrenheit on day x. So x is equal to 1 corresponds to January 1st, x is equal to 365 to December 31st. Use a calculator to estimate the temperature on the following days. Okay, so here is that function, the graph of that function, but the domain is restricted to 0 to 365. And again, you can think about the temperature, how the temperature varies cyclically through the winter and summer, or even winter, spring, fall, summer. That's like fundamentally periodic, right? Well, when you think about anything that's like fundamentally periodic, you're thinking sinusoidal distribution. So the temperature is low on January 1st. We're in the winter. Then temperature starts to rise. Then we get to the summer, and then temperature starts to fall back down until we're back in December, January. And then this same pattern repeats over and over and over again. Now you might wonder, well, yeah, but what if there is external factors like climate change? Then you can't use a sinusoidal distribution then? No, you can apply adjustments to sinusoids to account for external factors. You could have it damp down, but the foundation's still going to be sinusoidal. Okay, so let's see. We've got sine of, we're in radian mode, 2 pi over 365 times x minus 91. 21 times this. And then this plus 37, and we're going to store this as an equation E. Okay. So we want to plug in E with X is equal to day 74. So 30.9 degrees Fahrenheit. Okay, now day 95. 38.4. Okay, day 200. 57. Okay, so we got 1. Let's use this year. Okay, now let's test this. March 15th. Okay, so we want to do this minus this, but then add 1. Because like if we were doing January 2nd and we subtracted January 2nd from January 1st, we'd get 1, but we want 1 plus more than that. So 74. There we go. That's right. So now what about April 5th? So this minus this plus 1, 95. Yeah, there we go. So now June 25th. Is day 176. So about 57.9. Okay, October 1st. $274. So 36.8. Okay, and then December 31st, that's the 365th day. $16. Okay, there we go.